So as I mentioned, we're going to apply this idea of group action specifically to regular polyhedra. Right. Now, a polyhedron can be thought of as a collection of faces, edges, and vertices. Think of a cube, for example. You go down here and see the picture. You've got 1, 2, 3 faces visible, 3 faces in the back. You've got the vertices, 1, 2, 3, 4 on the top, 1, 2, 3, 4 on the bottom, and you've got edges. Turns out there are 12 edges. You can count them all. So we're considering polyhedra in this way. And a rotation will always take faces to faces, edges to edges, and vertices to vertices. So I should say a rotational symmetry. A rotation that takes that polyhedron to itself will always take like structures to like structures. Okay. So we're going to introduce two key ideas about rotation: G-equivalence and orbits. Now these two ideas are related. Basically, if two structures are G-equivalent, then they're in the same orbit. And you can see this word equivalence. That indicates that we're talking about equivalence classes. So this is a notion very close to equivalence classes that we had in the previous chapter. All right, so let's make these notions clear. First of all, we have to define some notation to explain what we're doing to a cube. So here's our cube here. Notice that we have three axes, x, y, and z. We've arranged it this way. The x is this way, and the y is this way, z is this way. This is what's known as a right-handed coordinate system. If you take your right hand and put your index finger along the x, and then curl it towards the y, your thumb will point up towards the z. So this is called a right-handed coordinate system. Now we're going to want to look at rotational symmetries, and we need a way to describe those. So we're going to describe three fundamental rotational symmetries. Now if you just think about the rotation around this axis z, there's actually four rotational symmetries. You can rotate 90, 180, 270, or 360. Of course, 360 is the same as the identity. But just think of those four rotations twirling around this axis z. We have four rotations. These four rotations are all multiples of what we'll call RZ. RZ is the counterclockwise rotation of 90 degrees around axis z. Okay, so just 90 degrees. It would take this edge to this edge here, and it would take this edge to this edge here, and so on. So that's what my RZ is. Now, Rx and Ry are similar. Rx is going to be the counterclockwise rotation around the positive x-axis by 90 degrees. So Rx would take this edge to this edge, and so on. Notice that Rx leaves this face in the same place. Now, the face is rotated, but the face still occupies the same place. So we would say that Rx leaves this face unchanged. Similarly, Ry is the counterclockwise rotation about the positive y-axis. So it's going to be this way. All right, so we have a way of describing rotations about these axes. Now we also want a way of representing the parts of the cube. Let's denote the faces. Now notice that if you take any axis x, there's two faces perpendicular to that axis. There's the face through the positive x-axis, and the face in back here that you can't see through the negative x-axis. So we call those two faces x plus and x minus. Same with y. Y plus is here, y minus in back. Z plus on the top, z minus in back. Right? So notice that if I rotate, this face x plus is going to go to one of the other faces. And it shouldn't be too hard to convince yourself, if you get a cube model, that I can find a rotation that takes this face x plus to any of the other faces. We can also compose rotations. For instance, Rx, compose Rx, or Rx squared would be the rotation by 90 degrees, followed by another rotation by 90 degrees about this axis, which gives us a rotation by 180 degrees. All right, so that's our basic notation. All right, so here you're supposed to give different rotations. Now, when you give a rotation, you should give it in terms of the R, X, R, Y, R, Z. We got those 3 rotations specified, and you can specify any rotation that takes one face to another in terms of a composition of rotations. Right? Now here we introduce a notation for the cube's vertices. For instance, plus 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 represents the vertex where x is greater than 0, y is greater than 0, z is greater than 0. All right. So you should be able to figure out rotations that take plus 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 to some other vertices. All right. So why don't I do an example of one of these so you get some idea of what's going on. Let's consider first the one that takes the bottom face z minus to the face x minus. Let's see how we could do that. All right, so z minus is the face on the bottom, and I need to take that to the face x minus. Now, if you think about what's going on, if I simply rotate this cube counterclockwise around y one time, that's going to take z minus to x minus. So ry is the rotation that takes z minus to x minus. All right, now you may have to do more complicated rotations to get these other ones, but that's the basic idea. You may have to compose more than one rotation to get there, but the bottom line is if you compose multiple rotations, it's still a rotation. Right? Now let's do the first one of these examples. Suppose I want to take the vertex plus minus minus to plus plus plus. Plus minus minus to plus plus plus. What does that mean? That means the x is plus, y is minus, z is minus. So where is that vertex? X is plus here, so it's one of these vertices. Y is minus, so it's one of the 2 in the back. And z is minus, that's the one right here. That vertex there is the vertex we're starting with. And we want to take that vertex to plus plus plus. Now to get this vertex up to here, if you think about it, all I need to do is rotate this face 180 degrees to get this corner up to this corner. So that would be Rx squared. Rx squared takes plus minus minus to plus plus plus. And you can do the other vertices as well. So it's a good exercise to become familiar with these motions. All right. So we have a notation for faces and for vertices or corners. Now we need a notation for edges. So the edge, for instance, x plus z minus is the edge that joins these two faces. All right. So here, for the face x plus is this face here. Z minus is the face on the bottom. So x plus z minus would be this edge right here. All right, so that's a way of denoting edges. This edge here, for instance, would be z plus y plus, because it is the intersection between the face z plus and the face y plus. All right, so that gives me a way to specify vertices. All right, so your first, edges. So your first task is to list all the edges. Then you want rotations that takes this edge to each of the other edges. Since there are 12 edges, there's going to be 12 rotations. So for instance, the rotation that takes x plus y plus, well, let's try to do a hard one. What rotation would take this edge here to the completely opposite edge down at the bottom? Now, what's the completely bottom edge down at the bottom? The completely opposite edge down at the bottom? Well, that's y minus z minus. Okay, so y plus z plus, the opposite is y minus z minus. Now what rotation would take this edge down to that edge? Actually there's more than one, but I'll do just the easy one. If I rotate around the x-axis by 180 degrees, that would take this top front edge to the back edge. Okay, so you may have to do this with a cube model. But Rx squared would take z plus y plus z plus to y minus z minus. All right, so that gives me one example, and you can do the other edges similarly. All right. Now for a definition, let's read through this carefully. If a group G acts on a set X, and X and Y are elements of X, then X is said to be G equivalent to Y if there exists a group element such that Gx equals Y. We write that this way, X twiddle GY. So that means X is G equivalent to Y. We can write it this way. All right. Now, in this, you should think in our cube example that the G's are rotations and x and y are elements of the cube. So, for instance, I just finished mentioning that this edge x plus y plus can be taken to x minus y minus by a rotation. That means x plus y plus is g equivalent to x minus y minus. All right, so I could write that x plus y plus is equivalent, twiddle g, x minus y minus with a bar over it. Okay, so you can see that basically edges are equivalent to edges, corners are equivalent to corners, and so on. Okay, this theorem actually proves that G equivalence is an equivalence relation. You can read that theorem. And since you have equivalence relation, this partitions the set X into equivalence classes. In particular, if you think about the exercises we've done and the way that the cube is set up, if we think of a cube as consisting of faces, edges, and vertices, each one of these three sets are disjoint equivalence classes. And their union is all of X. All right? So each one of these sets is called an orbit of X under G. So orbit is simply another name for a G equivalence class. Now, if an element X, if a particular element little x of big X is in the orbit, we can denote that orbit by big O of little x. Now, of course, if the orbit has more than one element, then you can express this orbit in different ways. Okay, for example, you look at this example down here. If we take G as the permutation group, which is a subgroup of S4, this is not all of S4, but it's a subgroup of S4. And these permutations act on the set 1, 2, 3, 4, 5. All right, now X is a G set because it shuffles these entries around. Now, if we look at these permutations, this permutation takes 1 to 1, this one takes 1 to 2, this one takes 1 to 3, this one takes 1 to 1, this one takes 1 to 2, this one takes 1 to 3. So, in fact, the permutations only take 1 to 2 or to 3. Okay, so that means that 1 is in the same orbit as 2 and 3, but 1 is not in the same orbit as 4 or 5 because there's no permutation that takes 1 to 4 or 4 to 1. Okay. Now here I've also noticed that if 1 takes to 2, there's also a permutation that takes 2 to 1. For instance, this permutation takes 2 to 1. And 1 goes to 3, there's also a permutation that takes 3 to 1. This one takes 3 to 1. So we see that G equivalence is an equivalence relation, and this set 1, 2, 3 is an equivalence class. I could call this O of 1, or I could call it O of 2, or I could call it O of 3. And this one's called O of 4 or O of 5. There are two distinct orbits in this example. And here's another example for you to